While preparing an ALMA proposal using the observing tool, or OT, you noticed under Control and Performance something called the Maximum Recoverable Scale, and a question asking about the largest angular structure in source. What are these? We're all familiar with the concept of angular resolution. This is the smallest scale structure that can be resolved by a telescope, and for single-dish telescopes, this is inversely proportional to the width of the mirror. For an interferometer, however, it is the longest distances between antennas that determine the angular resolution. A smaller mirror, or antennas closer together, can resolve only larger structures. Unlike a large single mirror, where all size scales are sampled on the sky down to the angular resolution of the mirror, an interferometer can only sample structure on the sky determined by the projected distances between pairs of antennas. These antenna pairs are called baselines. Bigger baselines sample the smallest scale structures, intermediate baselines sample the intermediate size scale structures, and the smallest baselines sample the largest scale structure. Structure in the sky larger than that detected by the smallest baselines is simply not detected at all. The largest scale structure that can be detected by an interferometer is the maximum recoverable scale mentioned in the OT. To see qualitatively what this means, let's look at a familiar image, like this one of a spiral galaxy, and see what it would look like if observed with an interferometer. Ignoring the fact that this is an optical image, let's pretend that we're observing it with ALMA. Now, here's a simulated ALMA image. Notice the difference. If we subtract the observed image from the true sky image, we see those parts of the image that are missing because of the maximum recoverable scale issue. There is no information in the observed image about structures larger than this maximum recoverable scale. How does this affect your proposal? You will need to know both the smallest angular scales, that is, the angular resolution, as well as the largest angular scales in your targets that need to be detected in order for you to carry out your science, and to fill these values into the OT. The angular resolution determines the largest baselines needed, and the largest angular scale determines the smallest baselines. With 50 antennas giving more than 1,200 baselines, the ALMA 12-meter array can detect a wide range of size scales. But if very large size scales are needed, it may be necessary to combine observations with the ASIAA 7-meter array, whose antennas can be located very close together, and with the total power array, a set of 4 12-meter single-dish telescopes to get the very largest size scales. Now let's look at an example. You might be interested in using ALMA to look at 1 arcsecond angular resolution at all the CO3-2 emission from molecular clouds within the spiral arms of a nearby galaxy. At the distance of this galaxy, the clouds each have an intrinsic size of about 10 arcseconds. Since the CO emission will only originate from these clouds, we want an observation that will be sensitive to a range of scales from 1 arcsecond to 10 arcseconds. In this example, we see that the most compact configuration will give us nearly the target resolution of 1 arcsecond, but the maximum recoverable scale is only 7.1 arcseconds. With these observations alone, we wouldn't be able to recover all the emission from the target clouds. To recover all the emission from these clouds, we can, however, choose to use the ASIAA as well. This is just one idealized example based on a source at the celestial equator. For many problems, it is not necessary to have full spatial scale coverage. It is up to you, the proposer, to decide what is the most effective and economical way to use the power of ALMA to address your science.